Okay, Unit 4, Section 4.9, Verifying Trig Identities. First thing, if you haven't checked the UC Scout video that I uploaded before, and I mean, you're supposed to watch it before you come to my Zoom, but if you haven't, I strongly recommend you guys to watch that one later, okay? Because she explains the basics of verifying trig identities, and I focus more on actual problem solving. I assume that you guys know the basics of the trig, the verifying trig identity. So if you just don't watch both of them, and then probably you will miss something, okay? All right, and let's jump right into example number 1. All right, so the example number 1 is not really verifying, and then this one is only asking us to rewrite the given expression. So we can start a little bit late. But before we move on to this, and I want to emphasize that basically verifying is not solving equation. The big difference is when you get to solve equation, that you can manipulate both sides, you can manipulate one side, you can manipulate all around the given equation. But verifying identity, of course, you're gonna have left side totally looking different from the right side, but you have to prove they are eventually the same as it was indicated with the equal sign. So the only one principle that you have to remember is you cannot rewrite or manipulate both sides at the same time. Because we're so used to use both sides of equal sign a lot, and then this is common misconception that I repeatedly see every year that I start this part, the verifying trig identities, and a lot of students just start changing something in the left-hand side and changing something in the right-hand side at the same time. But that's not gonna work because we have to pick one side. And over the multiple steps that we showed step by step, it's becoming the other side. So if you manipulate both sides at the same time, and then they're never gonna meet anywhere. Does it make sense? So you have to remember that, right? Okay, and once we start the example number 2, and then I will show you how you officially start the verifying. Okay, so then let's go back to example number 1 and rewrite 1 over sine x times cosine x right here. So this is simple. Then the only one condition they're asking us to do is without using fractions. So the given expression is fraction, but we have to rewrite whatever the given fractions with non-fractional form. So the first thing that I notice here is it's 1 over sine x times cosine x, right? Then in algebra, we do 1 over a times 1 over b is 1 over a times b. 1 times 1 and then a times b, like that, right? So then this must be 1 over sine x times 1 over cosine x before, right? Then it could have been 1 times 1 on top and sine times cosine being sine x times cosine x on the bottom, right? Then if you separate this 1 over sine and 1 over cosine, and instinctively we can see them as the reciprocal property and reciprocal identity. So the 1 over sine is cosecant of x. 1 over cosine is secant x. So this could be the answer, But you will not see this answer choices directly, but remember the multiplication has commutative properties, so it's totally fine that we can rewrite it, rearrange. So secant x times cosecant x there, and this must be one of the answer choices given. Okay, so that was easy and simple. Okay, so as you see, when you check your notes, and the next page is a step-by-step answer there. Okay, then if you guys don't have any questions, and then we'll move on to example number 2. Example number 2. All right, so finally we get to this part, verifying trig identities. And once again, we have to pick one side. And there's no absolute rule which side is better. But generally, more than 90%, I think, it's better for us to pick the more complicated side so that every step that we simplify in going towards this simpler side given. It's better simplifying than creating something from simple expression to just like expand. Like, so creating something from the scratch or creating something expanded from the simple one is harder, if you just understand what I'm saying, right? So usually it might be easier for you guys to pick complicated one and figure out the way that we can rewrite and simplify so that we are directing, we're going towards the other side that has a simpler form as given, right? So that being said, we can pick left-hand side, right? Then official way of starting verifying trig identity is this, because they have both sides, and then one is left-hand side and the other side is the right-hand side, and it starts from this. We just write, so we are selecting the left-hand side, and then we can start with LH, meaning left-hand side. Yeah, okay, then left-hand side, and then let's notice the first step for us to do is factoring common factor. How do we know? Because every term in the left-hand side, including cosine, cosine, cosine. So from earlier sections, and we did this practice a lot, so we can factor this common factor first. So left-hand side, the first step is factoring cosine x out. Then I factored cosine x out of cosine x, and there's 1. Then I'm factoring cosine x out of 2 cosine tangent square of x, and it's going to be 2 tangent square of x. Then the third term, if you factor cosine out, there's tangent power of 4x, right? Then here again, I leave the right side alone until I do have the form that I given on the right side from the side that I'm manipulating. So I'm not even copying it down, right? So I just ignore. Then now I have to look for another way to simplify inside of the parentheses. But what we notice there is actually tangent square of x squared will be tangent x power of 4. If then, we can utilize a trinomial factoring method. So it's gonna be cosine x outside. Then this is tangent square of x squared. Then I'm just rearranging the terms for the convenience of the trinomial factoring. Then 2 tangent square of x and plus 1 here. Okay. And now I'm ready to factor the inside. So copy cosine x here. And then now let's prepare 2 parentheses side by side. I will use the happy cat. So the first term is tangent square of x squared. So now I have tangent square of x here, tangent square of x there. Then notice the factor of 1 is just 1 times 1. So I can put 1 and 1 there. Then based on the given sign, they must be positives. Then I factored. This is the happy cat here. Happy cat method there, right? Then we notice tangent square x plus 1 is one of the Pythagorean theorem, and I think it's a group 2, right? So it's a group 2. Then we can rewrite each one into cosine x, copy down. Tangent square x plus 1 is equal to secant square x, and there's another. So one more secant square x. Then this is cosine x times secant square, so it's power of 4, right? Then now what I'm supposed to have is a secant cubed. Then it's already there. How? Because remember cosine is 1 over secant x and then secant power of x. Then this is over 1. And then 1 of secant x will cancel this, and then this is secant cubed x there. So now I finally match everything, reduced down to secant cubed x right there. Then since I'm done, I showed you it's gonna be equal to right hand side, and then I can initial the R and H. Then there's a little square. And then this is mathematical notation that shows that you are done with the proving. Okay, this is the official way for a mathematician would do at the end of the proving anything. Okay. Okay, how was our first verifying trig identities? Is it good? Overwhelming? Too much? I hope you guys get familiar to this. So we will have 3 more examples, and as you just see more examples, and as you watch videos more times, and if you practice more, and hopefully you get used to this method. Okay, let me know if you guys have any questions. So I will erase this. And also example number 2, and I already put the step-by-step explanation next to it too. And I even put the happy cat explanation there. So later if you check it back, and then it's gonna help you, okay? Then example number 3. Then verifying trig identities. Now, left-hand side, right-hand side, we have to pick. And left-hand side, yeah, left-hand side is, there's room for us to simplify. So probably we will go with that one, right? Okay. Then notice we have fractions here. Then let's recall. If we have 1 over 2 minus 3 over 5, the next step that we are supposed to have is we have to match the denominator. So if they don't have any common factor, so we can just multiply them. So then 2 times 5 will make 10 as a common denominator. But in order to do that, we have to multiply the first fraction with 5 over 5, the second fraction with 2 over 2. This is just normal way for us to multiply and manipulate two fractions that have different denominators, right? Okay, then the top will be 5 times 1 minus 3 times 2, and then you can go from there. So recall this method, and then we're gonna apply this one exactly onto two fractions subtracting together. Cosecant x over cotangent of x minus cotangent x over cosecant x, right? Okay, so then left hand side. Then since the denominators, one denominator is cotangent x and the other denominator is cosecant x, and we will multiply them just like we multiplied 2 and 5. Then now we have cotangent x times cosecant x here. Then I have to multiply the first one times over cosecant x over cosecant x, just like we did 5 over 5 in the first one. Then the second one will be multiplied cotangent x over cotangent x. Then the first numerator is cosecant times cosecant, which makes cosecant square of x and minus. Then second numerator will be cotangent x times cotangent. It's cotangent square of x. Then now notice something that we can use from the numerator. Again, we will utilize some of this. So group 1, group 2, group 3. And notice group 3 Pythagorean trig identity includes cotangent and cosecant. Then, since we have cosecant minus cotangent square, so here, imagine that you subtract cotangent square theta from both sides. Then this will be cosecant square theta minus cotangent square theta, and this cancel is equivalent to 1. Then it's easy. Actually, the numerator on the step is nothing but just 1. So now 1 over cotangent x times cosecant x there. Then let's see what we have on the right side. We have tangent x over cosecant. So we're not quite there. But I do see some possibility from my step because there's a cotangent and cosecant. And one thing really good is we do have cosecant on the denominator. And then that's our goal. That's our direction to go. So just like we did in example number 1, and then we can separate it. It's 1 over cotangent x times 1 over cosecant x. Then once I separate it, I can see it better. 1 over cotangent is what? Tangent. So it's a tangent x times 1 over cosecant x. Then this is tangent x over 1. Then if I multiply top and top and bottom, then it's going to be tangent x on top, cosecant x on the bottom. Then that is what I have on the right hand side. Cool. Any question? So this is really important that you utilize this Pythagorean theorem, okay? Then as usual, once you move to next page, and it will come with all these steps, okay? Then example number 4. Okay, example number 4 is a little bit lengthy. Then we just look at both sides. And it's really hard to tell which one is more complicated than the other. They're about the same. So I guess it doesn't matter which side to pick, right? But I just wanted to show you it's totally fine. And once you started with one side and then it doesn't really give you the direction that you would like to go, and you can pick the other side. So I intentionally picked the left-hand side first. Then let's see how it goes. Then here we have left-hand side. And what I can do first is I noticed first term has a cosine square and there's sine as well. So it might be a good idea that we can rewrite everything in one language. So since I can utilize cosine square is 1 minus sine square, and then I can rewrite that part. So then let's rewrite it. Based on what? This again. So cosine square theta is 1 minus sine square. Then this is negative 2 times of it. So negative 2, 1 minus sine square x. And then I copy sine x plus 1 there. Okay, then instinctively everybody loves how like distribute, right? So right there we can distribute. Then it's gonna be negative 2 plus 2 times sine square of x plus sine x plus 1. Okay, then I noticed there's negative 2 in the beginning and there's 1 and then they're numbers and then I can calculate them. So then it's going to be 2 sine square x and then it followed by sine x. And negative 2 plus 1 will make negative 1. Is it factorable? Yeah, I noticed that. I noticed the trinomial factoring structure there. So let's factor it. Then two parentheses side by side. The factors of 2 sine square x is 2 sine x and sine x. And factors of 1 is again 1 and 1. Oh, I copied it. So remember negative 2 plus 1 is negative 1. I don't know why I put positive. Okay. Then negative 1 factor is 1, negative 1. But we have to make positive 1 sine x. So now this has to be positive this has to be negative. So that this is negative sine x, this is positive 2x, and then this is happy cat again. Then let's see. So I factored it, and then I have 2x minus 1 and 2 sine x minus 1 and sine x plus 1. But it doesn't really give me any further steps to benefit this direction. It's not really squared, no possibility for the Pythagorean theorem, and I don't know what we can do. Then I'm baffled. Embarrassing, but it's okay. So if one side is not really working, we have another choice. Okay, then let's go to the right-hand side. And right-hand side. Then that's gonna be, well, what can I do? Should I factor? No, all three terms don't have the common factor. But at least I can rewrite tangent into sine and cosine language. So we notice the tangent here. Then right-hand side will be sine square of x minus cosine x. Then tangent is sine x over cosine x and minus cosine square x. Then fortunately, we can cancel cosine and cosine. Then it's sine square x minus sine x minus cosine square x. Then now I have two sine term and then one cosine term. And why don't I rewrite everything in sine only? So then sine square x copied minus sine x, and then this is negative in parentheses 1 minus sine square x from here. Then sine square x minus sine x, and then distribute negative 1 plus sine square x. Then sine square x, they add to be 2 sine square x and minus sine x and what is it? And minus 1. Then it's very similar to left-hand side, so it's almost successful, but somehow all the terms are the same, but the signs, positive and negatives, but we can still make it. So imagine we multiply everything by negative 1, so it's going to be negative 2 sine square x, positive sine x, positive 1. It is original left-hand side, so it is left-hand side there. So started from right-hand side, second trial. Then we successfully rewrote all the way to the left-hand side. Cool? Okay. Then you can see I left both of the trials here. So the first one didn't work, but second one, the right side, worked. Okay, so then the last one is a very special case. And as I usually emphasize that you have to know the square, the difference of squares come in handy so many times. And now you have to add one more into your toolbox. Now, without knowing this, it's gonna be really hideous. So that's why I just give you this format here. It's called difference of cubes. Difference of cubes. It's very similar to difference of squares, but if you see the format following, and then it takes a little bit further steps there. But if you know this, then it's really easy. And the next step, it shows directly from that formula, it rewrites each part based on the formula. Then you notice cosine square x, sine square x added to be 1, and then you rewrite that part. The yellow highlighted part will be just equal to 1. So here and there, it's adding, right? So it becomes 1. Then just rearrange that parenthesis will get you to the right-hand side. So without knowing, it's really long way to go. But knowing this format, and it's just easy peasy. Okay, so that was all 5 examples. And any question